All right, thank you everyone for coming. My name is Talha Agcayazi. I'm from the NC State University, and today I have a talk for you about biobotic sensor networks and how to acoustically localize them. I'll go through the motivation, give you the introduction, tell you the hardware, software of what makes this localization system possible, and then I'll tell you about the results that we got and then conclude my presentation. So what do we call biobots? Biobots are systems that have biology and electrical engineering, or electronics combined together. I work for the iBionics laboratory in NC State University, and for 5 years we've been working on biobotic systems and especially cockroaches. So I encourage you to go online, type NC State cockroaches. For 5 years we've been working on this. So this one is specifically about mapping the environments with biobots. So cockroaches, we envision their goal to be environment sensing. So think about earthquake environments. Under the rubble, you have cavities, and mapping those environments is really important for the first responders. So how do we remotely control these cockroaches? Turns out cockroaches navigate with their antennas, and they use these antennas as the main sensor. So what you can do is you can put an implant into their antennas and then stimulate them the same way that a rock, for example, would stimulate them when the cockroach moves into it. And the cockroach thinks that there's an obstacle towards whichever antenna that you stimulated it. So if you stimulate the right antenna, it turns to the left, and vice versa, it turns to the right. So we've discovered that PWM pulses work best for this. So what's the hardware, or what's this biological system really look like? We have the PCB over there. It houses a Texas Instruments CC2531 chip. We have it's connected. You can see the implants have it's merely just, I can't say it's an easy process, but it's electrodes connected to the antenna. And then you control the cockroaches. It has a RF transceiver, and you have enough memory. Now let's come back to our motivation. So you have this rubble. How do you localize and then map this environment out? We have an access point. This is our envisioning. We have an access point. We have anchor nodes that we know exactly where they're located. And then we have a sensor network under the rubble made out of cockroaches. And some of them can't directly be accessed by the anchor node, so we have a network in there carrying the information. So we envision two ways of localization. One is range-free, one is range-based. Range-free is just if you have communication between the target node and the receiving node, you know which area it might be in. And in range-based, you need a distance sensor from the receiving node and the target node, or the transmission node and the target node. But with this, you can actually triangulate the position and find the final position of the node. So we're going for range-based, but we need a distance sensor. And for an RF transceiver, the first thing that comes into mind is the RSSI. The RSSI is basically a measure of power present in the received radio signal. It deteriorates over distance, so it seems like the first destination to go for a sensor. But actually, it has multipath path loss, constructive, destructive signal interference really play an effect. So RSSI-based systems, they have limited precision. So this is when we move back to acoustic signals, which take time as they're moving through space. So using the speed of sound, we can actually calculate how far this target node is. So let me jump into the hardware that we developed for this. This hardware is slightly bigger than the other one. It contains the battery connections. We got the same microcontroller. We have an analog front end, one omnidirectional microphone connection, one unidirectional microphone connection, and one fixed buzzer. So what are the embedded system programming necessary to go into it? Before then, let me tell you about the limitations of the software. First of all, we have the signal decreases really fast due to off-the-shelf components and miniature size. Secondly, there's no individual units, or individual units don't have uniform characteristics. So the solution to all of those is in these three bullet points. We have a preamplifier design to increase the SNR, some signal processing, and then we have range calibration to compensate for microcontroller time delay. So this is the preamplifier design. It has an active bandpass filter, a coupling capacitor, and another amplifier. In total, it has 10,000 time amplification, which with cutoff frequencies very far away from the transmitted signal. This is an example of the transmitted signal. You can see even though we have a lot of amplification, it's really buried inside the transmission or the received microphone ADC results. At about 1,000, you see the sound coming in, but we have to actually do a moving variance time series to actually see what time that data actually comes in. We actually also had to calibrate for microcontroller time latency. So this data over here is uncalibrated data. The blue one is uncalibrated data, and then we fit a trend line over it to find the relationship between the estimated distance versus the ground truth distance. And with this, we can decrease the error from 30 centimeters plus or minus 30 centimeters down to 10 centimeters. And this is the CDF decreasing before and after calibration. Now let's look at the results for this paper. So we had 6 different nodes. 4 of them we knew the positions, 4 of them transmitting, and 2 of them receiving. 6 and 5 were receiving, and you can see the dotted lines over there are the estimated positions for the nodes, and for the nodes 5 and 6. And the red is actually the real position, ground truth. So you can see how well it's fitted together. I think for this, the estimation error was about 10 centimeters as well. So that's conclusion. We designed, implemented, and evaluated acoustic localization system for this network of Biobots. Next up, we'd like to actually join together RSSI data and acoustic data to get a better distance reading. And then we'd also like to leverage unidirectional microphones for positioning and heading detection. So that's all. If you have any questions, I can take them now.